Welcome to NPTEL online course on machine learning and deep learning, fundamentals and applications. In my last class, I explained the concept of the deep learning and also I explained the concept of the convolutional neural network, that is CNN. For the training of the network, I can employ the backpropagation training algorithm that already I have explained. And if I increase the number of layers of a particular network, it is expected that the performance of the network may improve, because the network can extract more number of features from the input image. That means I will be getting more representations of the input data or the input image with the help of more number of layers. So I am repeating this. So if I increase the number of layers of a particular convolutional neural network or the deep architecture, it is expected that the performance may improve. But practically it is not happening in many cases because of the problem of the vanishing gradient. The opposite of the vanishing gradient is the exploding gradient. So today I am going to discuss this concept, the concept of the vanishing gradient. So before explaining this concept, I will be explaining the concept of the single layer perceptron, and after this I will be explaining the concept of the multi-layer perceptron and also the backpropagation training algorithm. And after this I will be explaining the concept of the vanishing gradient problem. So let me begin this class. So in this case I have shown one single layer perceptron SLP. So we have the input signals x1, x2 up to xm, you can see in the figure. So I have the input signals and you can see I have shown the summing junction and you can see the connecting weights. So WK1, WK2, WKM, these are the weights, the connecting weights between the input node and the summing junction. And also we are considering the bias input. BK is the bias input and you can see these are the input signals. So this is the single layer perceptron. So we don't have any hidden layers, we have the input layer and you can see the output, that is the output node, and we are considering the activation function. So at the kth node, the input xj, all the inputs are multiplied by their weights, the corresponding weights, along with the bias bk are sum. So already this concept I have explained. So I have to consider weighted inputs. So input is multiplied with the corresponding weights and we have to sum up, and also we have to sum the bias. So we have to consider bias also. At kth node, the inputs xj's multiplied by their weights, the weights are wkj, along with the bias bk are sum. And we are considering the activation function phi that controls the magnitude of the accumulated output. So why I need the activation function, that already I have explained in my artificial neural network class. So this activation function phi controls the magnitude of the accumulated output. So mathematically how to determine yk? So yk is the output, so that is nothing but phi vk. So vk is nothing but the accumulated output. So that is nothing but first what we are considering, the inputs are multiplied with the corresponding weights plus bias, the bias is the bk, so it is sum up. So j is equal to 1 to m because we are considering m number of input signals x1, x2 up to xm. So this is the mathematical representation, and in the vector form I can write in this form, that is nothing but w transpose x, that is the dot product, plus bk, and bk is the bias input. So this is the concept of the single layer perceptron. So in this case we are considering this activation function, phi is the activation function and vk is the accumulated input. So the output of this is 1. If you see the output is 1 when the vk is greater than 0, that is the w transpose k plus bk is greater than 0, that is nothing but 1, the output will be 1. Otherwise the output will be 0. So for this we are considering the step function as an activation function. So here I have shown the step function as an activation function, and the bias is considered to change the position of the decision boundary. but I cannot change the orientation of the decision boundary. Only I can change the position of the decision boundary based on the bias value. So bias changes the position of the decision boundary. So this is the concept of the SLP, the single layer perceptron. Now during the training, what will happen, you can see, because already I told you SLP is good only for the simple classification problems, and if the problem is very simple, and suppose the problem is the linearly separable classes, then we can employ the single layer perceptron. So here you can see I am considering the inputs x1 d1. So corresponding to x1 input, the desired output is d1, and corresponding to xn, the desired output is dn. So because this is the supervised training, so corresponding to particular input, what is the desired output, that I know. So corresponding to x1, the output is d1, that is the desired output. Corresponding to x2, the desired output is d2. Like this, I have the training samples. So during the training, first I have to randomly initialize the weights, and after this we have to compute y. That y I can compute, that is the output we can compute. So that is nothing but W transpose dot xj. So we are having this equation, the input is multiplied with the weights, and we are considering the activation function. The activation function is phi. After this we have to update the weights. The weight wi t plus 1, that is the weight in the t plus 1 iteration, is equal to wi t, that is the weight in the t8 iteration, plus we are considering the error. The error is nothing but the desired output minus actual output, that is considered. That is the error, because already I told you during the backpropagation training, the error is backpropagated to the input. So this dj minus yj, that is nothing but the difference between the desired output and the actual output, that we are considering, and we have to minimize the error. So for this I am updating the weights by considering this weight updation rule. So this is the weight updation rule we are considering. So I have to do the iterations until the cost function, and the cost function already I have defined, that is nothing but the difference between the desired output and the actual output. So until a particular convergence condition is not obtained. So you can see the error should be less than the parameter. The parameter is gamma. So gamma is the user defined parameter, that is the threshold, and if the cost function is less than this gamma, then I can stop the iteration. So by considering this backpropagation training, we can find the decision boundary between the classes. But the problem is, it can be employed if the problem is very simple. The problem means the pattern classification problem, and the classes should be linearly separable. Then only I can apply the single layer perceptron algorithm. So for complex tasks, I have to consider multi-layer perceptron, MLP, that is the feed-forward network with hidden layers. In SLP, I don't have hidden layers, only input layer and the output layers are available. But in case of the MLP, I have to consider hidden layers between input layer and the output layer. So the drawbacks of the SLP, so the output of a perceptron can take only one of two binary value. So either it is 1 or 0. So it is not also this SLP not able to solve complex problems, the complex pattern classification problems, and picks up many solutions of varying quality. So that already I have explained in my previous slide. So it is very difficult to find the best decision boundary between the classes. If the vectors are not linearly separable, learning will never reach a point where all the vectors are correctly classified. So if the problem is not linearly separable, then this SLP cannot give good accuracy. And the problem is the misclassification. So if I consider a very complex problem, and if the samples are not linearly separable, then I have to consider MLP, the multi-layer perceptron. So let us move to the next slide. So in this figure, I have shown the concept of the multi-layer perceptron, MLP. So input is first transformed using a learned nonlinear transformation. So maybe we can employ some nonlinear transformations for mapping. That concept I have explained in case of the radial basis function. So this allows nonlinearly separable input data to become linearly separable. So I have to consider nonlinear transformations of the input data, and if I do this transformation, the data will be linearly separable. So that concept I have explained in case of the radial basis function. And in the figure I have shown one single hidden layer MLP. So you can see the input layer. So this is the input layer. So the nodes are x1, x2, x3, and we are considering one hidden layer, and the nodes are h1 and h2, and we have the output node, that is y. So it is a very simple network, that is a single hidden layer MLP we are considering. So what will be the output at the node y? So we are considering the activation function phi. Now I need to determine the output of the node y. So by considering this equation, that is nothing but we are considering the activation function phi, and weight is multiplied with the input. The input is hj, and the corresponding connecting weight is wj. So I am getting the output y, that is nothing but the phi, that is the activation function. The wj is multiplied with the input is hj. So this is my input. So this expression, the phi summation wj into hj, that can be represented like this: phi wj, hj can be represented like this: summation wij into xi. Because what is the output? What is the output in the node h1 and h2? So that is nothing but the input xi is multiplied with the corresponding weights. The weights are wij. So corresponding to hj, that is the output, my input is xi. So xi is multiplied with the corresponding weights, that is the connecting weights, wij, and we are considering the activation function phi. So I can represent like this. Now I have to optimize the loss function jw. So that is nothing but the minimum, and we are considering the difference between the actual output and the desired output. So dk is the desired output. So that the loss function we are considering. So by considering this equation, we can determine the actual output, and we are considering the desired output, that is the dk is the desired output. So we can consider this loss function. So the dk is the target to the output node yk. So dk is the target to the output node yk. So in this case the k is equal to 1, because we are considering only one node in the output layer. So we can consider the backpropagation training for weight updation. So move to the next slide. So what is the backpropagation algorithm? So it has two phases. First one is the propagation, and another one is the weight update. So in the propagation, forward propagation of a training pattern's input through the neural network in order to generate the network outputs value. So we are getting the output values corresponding to the input patterns, the input values, and after this the back propagated of the output activations through the neural network using the training pattern target in order to generate the difference between the target and the actual output value. So that concept already I have explained. So that is the cost function, that is nothing but the difference between the actual output and the target value, that is the desired output. So that we have to minimize. For minimization of this, I have to adjust the weights of the artificial neural network. So we have to calculate the gradient loss function. So gradient value we have to calculate, because I have to find the minimum value. So that is why I am taking the gradient of this. And finally we are considering the weight updation rule. So that is nothing but wt plus 1 is equal to wt minus gamma, and we are considering the gradient of the loss function. So we are updating the weights, and this gamma controls the speed and the quality of the learning. So that means it controls the learning rate. So that is the parameter. The gamma is the user defined parameter, and it controls the speed and quality of the learning. So in this discussion, I am considering the sigmoid activation function. So activation function is sigma x, that is equal to 1 divided by 1 plus e to the power minus x. So one advantage of the sigmoid function is that the derivative can be easily computed for the sigmoid function. So here you can see I am just computing the derivative of the sigmoid function. The sigmoid function is 1 divided by 1 plus e to the power minus x, and you can see just I am taking the differentiation, and finally I am getting this expression sigma dash x, that is the first order derivative, is equal to sigma x into 1 minus sigma x. So you can see it is easy to determine the derivative of the sigmoid function. So that is why in artificial neural network we consider the sigmoid function. So during the weight updation, already I told you, we considered gradient descent algorithm. So that algorithm already I have explained in one of my classes. So you can see in y-axis we are considering the cost function, and w is the weight, and this point we have to reach, that is the global cost minima. So that point I have to obtain during the iteration, that is the global minimum. So suppose my initial point already I have shown, this is my initial weight, and if I take the gradient of this, then the gradient at this point will be in this direction, that will be the direction of the gradient. But to get the minimum I have to move in the opposite direction of the gradient. So that is why this minus sign is because of this. So I am moving in the negative direction of the gradient. So that is why we consider the negative sign, and this gamma is nothing but the learning rate. So if the learning rate is very high, then during this iteration, so this value may go to this point, this value may go to this point. Like this I have the oscillations, and for the convergence it will take time. But if I consider this gamma is small, then you can see this convergence, the convergence will be like this. So I am getting this one like this, I am getting this gradients, and after this I am getting this minimum point, that is a global minimum point I am obtaining. If I consider the gamma is very high, then the faster will be the convergence, but it may not be accurate. But if I consider lower gamma, then I will be getting the more accurate convergence during the training, but it will take time. So that is the concept of the gradient descent algorithm. So I am moving in the opposite direction of the gradient, and the parameter gamma controls the learning rate. The parameter gamma controls the learning rate. If gamma is high, then the faster is the convergence. If gamma is low, then the more accurate in the training, but it will take time for the convergence. Now I will show the mathematical derivation of the backpropagation learning algorithm. So here I am considering a multi-layer perceptron, that is the feed-forward network. I have one input layer, one hidden layer, and one output layer. So corresponding to this input layer, the inputs are x1, x2, x3, x4. These are the nodes of the input layer, and h1, h2, h3, these are the nodes of the hidden layer, and I have two nodes in the output layer. The connecting weights between the input layer and the hidden layer, that is wij, and the connecting nodes between the hidden layer and the output layer is wjk. So a single hidden layer ANN is considered for simplicity. So let us consider the derivation of the backpropagation training algorithm. So we can determine yk. So we are considering the sigma. Sigma is the activation function. The weight wjk is multiplied with the input. So input is h1, h2, h3. For the output y1, y2. So now we are considering the weight updation for the hidden and the output layer. So only this portion of the network we are considering. So inputs will be h1, h2, h3, and the output will be y1 and y2. So what is the yk? Yk is nothing but sigma summation I am multiplying the inputs. The input is H1, H2, H3 with the weights, the corresponding weights Wjk. So this expression I am obtaining by replacing Hj by this one. So what is Hj? Hj is nothing but the output corresponding to the input. The inputs are x1, x2, x3, x4. So in terms of this, I can write Hj. So Hj is nothing but sigma. If you see this part, sigma, and we are considering the input is multiplied with the connecting weights and it is sum up. That means we are considering the weighted inputs. And the cost function is again, that is the Jw, that is nothing but the desired output and the actual output. So we are considering Yk is the actual output and Dk is the desired output, that is the target output, and based on this I am formulating the cost function. So now I have to take the derivative of the cost function with respect to the weight, and in this case we have to do for two cases. One is for the output nodes and one is for the hidden nodes. So we have to do the differentiation with respect to the weight, and in this case I have to consider the output nodes and the hidden nodes. So you can see here in the output node I am differentiating the cost function with respect to the connecting weights. So the connecting weights are Wjk. So this is the connecting weights. So that can be written like this: delta Jw divided by delta Ink into delta Ink divided by delta Wjk. So what is Ink? That is the input to the output node Yk. So Ink is the input to the output node Yk. So this delta divided by delta Ink into 1 by 2 summation k is equal to 1 to k. So this expression I am getting, that is the nothing but the Jw, that is the cost function, and this part I am differentiating the Ink with respect to Wjk. So what is Ink? Ink is nothing but Wjk into Hj. So that is the Ink. So Ink we can determine, and that is nothing but Wjk into Hj. And if I take the differentiation of this one, so this will be this. So I am just taking the differentiation of this. This is the sigmoid function, and finally I am getting this expression. The expression is delta k Hj. So what is the delta k? Delta k is nothing but delta Ink minus dk delta dash Ink. So delta dash is nothing but the first order derivative. So this expression you can see, the very simple expression, and these mathematical steps you have to see how to derive this equation. Now at the hidden node we have to consider this one, the differentiation of the cost function with respect to the weight Wij. So Wij is nothing but this Wij, that is the connecting weights between the input nodes and the hidden nodes. So this I can write in this form. So that is delta Jw divided by delta Inj into delta Inj divided by delta Wij. So that is by the chain rule we are considering this expression. So that is by considering the chain rule I am getting this expression. So this Jw already I have defined, that is nothing but the difference between the actual output and the desired output, and this is nothing but what is Inj? Inj is nothing but it is the input to the hidden node. So that is nothing but Wij into Xi. So the input Xi is multiplied with the corresponding weights and it is sum up. So that is the Inj, and after this I have to do the mathematics. You can see the steps, all the steps. So just I am doing the differentiation, and finally I am getting the expression, that is the delta J into Xi. And what is delta J? The delta J is I am obtaining like this. So it is a very simple derivation, and in this derivation you have to see how to get this expression. So at the hidden node I am determining this, and in the previous slide at the output node we are determining this. So at the output node we are determining the differentiation of the cost function with respect to the connecting weights, and at the hidden node again I am determining the differentiation of the cost function with respect to the connecting weight. So connecting weight is Wij. So I am getting this expression. So now how actually we do the backpropagation training, so that illustration I want to show you. So this simple network I am considering, and the inputs are x1 and x2. In this network I have two hidden layers. So this is my input. So this is my input, and I have two hidden layers, and this is my output node. So how to do the backpropagation training in this case? So let us see. So you can see first I am determining y1, that y1 I can determine, that is the output y1 I can determine corresponding to this node. So y1 is nothing but f1 is the activation function, wx11 that is the connecting weight between x1 and the node of the hidden layer. So wx11 into x1, that is the x1 is the input, wx21, so that wx21 you can see the weight, the connecting weight between the x2 and the node is 1, the hidden node is 1. So wx21 into x2, so we are getting the value y1, that is the output in the hidden node 1 of the first hidden layer. So after this we are determining the activation, this activation we are determining. So that is nothing but y2 is nothing but the activation function f2, and we are just multiplying the weight wx12, you can see in the figure, into the input is x1, and wx22 into x2. So it is a simple equation, and we are determining the activation in the hidden neuron. We are determining the activation in the hidden neuron, and similarly the y3 corresponding to this neuron can be determined like this. So we are determining the activation or the output corresponding to this hidden neuron, and after this we are considering the second hidden layer, and you can see this activation or this output we can determine like this: f4, that is the activation function, w14 into y1 plus w24 into y2 plus w34 into y3. So that we are determining, and after this we have to consider the second, the node, this node we are considering, and we are getting the output is y5 we are getting. After this come to the last node of the output node, so that is the output node, and we are determining the activation, that is the output y is equal to f6, that is the activation f6, w46 into y4, w56 into y5, so that we are considering to get the activation at the output node. Now let us consider how actually we do the backpropagation. So we are determining the difference between z minus y. So y is nothing but that is the actual output we have determined, and z is suppose the desired output, that is the target output we are considering. So delta is nothing but the error, that is the difference between the target value and the actual value. So z is the target value and y is the actual value. So that difference we are considering, that is the error. So error should be backpropagated to the input to adjust the weights of the artificial neural network. So you can see in the previous slide we are determining delta. So this error is backpropagated, you can see. So delta 4 we are determining, that is nothing but w46 into delta. So we can now determine the delta 4. So corresponding to this hidden node we can determine the delta 4, and corresponding to this node, hidden node, we can determine delta 5. So delta 5 is nothing but w56 into delta. So you can see I am backpropagating the error. After this come to the next hidden layer. So if I consider this is the hidden layer, the corresponding this hidden node I can determine delta 1, that is nothing but w14 delta 4 plus w15 into delta 5. So I am moving towards left, that means I am moving towards the initial layers. Similarly corresponding to this node, this delta 2 is determined, and finally I am adjusting the weights the connecting weights between the input node and the hidden nodes, that is the WX11. So this is the updated weight, and W dash X21. So I have two weights, that is the corresponding to the this node, corresponding to this hidden node. I have two weights, connecting weights. So one is WX11 and another one is WX21. So these two weights I am updating by considering the weight updation rule. So by considering the weight updation rule, I am updating the weights, the connecting weights between the input node and the hidden nodes. So I am obtaining W dash X11 and W dash X21 I am obtaining. Similarly, I am getting the values W dash X12 and W dash X22. So all these connecting weights I am determining by this weight updation rule. So that is the weight updation rule for the back propagation training. And in this case, you can see I am just back propagating my error from the end to the beginning. From the end to the beginning, I am back propagating the error from the end to the beginning, and during this back propagation I am considering the gradient operation we are considering. So again, corresponding to this neuron, and we can determine the connecting weights W dash X13 and W dash X23 we can determine. So I am repeating this. During the back propagation, I am moving from the output side to the input side. That means I am moving in this direction, and I am computing the gradients. So I am computing the gradients, and based on this, the weight updation rules, I am updating the weights. So that is the concept of the back propagation training algorithm. And after this, again we are determining these weights W dash 14, W dash 24, W dash 34. So all the weights I can determine, and again W dash 15, W dash 25, W dash 35. So all the weights I am determining, and finally I am determining the weights between the output node and the hidden layer 2. So the weights between the hidden layer 2 and the output node, that is also determined. That is nothing but W dash 46 and W dash 56. So this we have determined. So this is the concept of the back propagation training algorithm. So let us consider one numerical problem here. The numerical on back propagation. So suppose in this network, I have shown one network, that is the feed forward network, and I have two inputs X1 and X2, and we are considering the bias input is one, but this is the bias input. So the bias values are B1 and B1. These two bias we are considering, B1 and B1. So it is a very simple network, and another bias is also considered. This is the bias input, and corresponding to this bias, the weight is B2. That is the bias weight is B2. And in this case, two input nodes, two nodes in the hidden layer, that is H1 and H2, and one node in the output layer, that is Y1. So corresponding to this input, X1 is equal to 0.05 and X2 is equal to 0.1. The target output is Y, that is equal to 0.01. And we are considering the sigmoid activation function. So that means corresponding to the input, X1 is equal to 0.05 and X2 is equal to 0.1. The target output corresponding to the node Y is 0.01. So that information is available. So first I have to initialize the weights of the artificial neural network, and generally it is randomly initialized. So initial weights we are considering corresponding to W1, W2, W3, W4, W5, W6, all the weights. So suppose the values are 0.15, 0.20, 0.25, 0.30, 0.40, 0.45, and the bias B1 and B2 are suppose 0.35 and 0.60. So these are the weights. And during the forward pass, that is the forward pass, first I have to do the forward pass, and after this I have to do the backward pass to adjust the weights of the artificial neural network. So first I am computing INH1. So that is nothing but corresponding to this hidden layer and the hidden node, we are determining the INH1, that is nothing but W1 into X1 plus W2 into X2 plus B1 into 1, bias input is considered B1 into 1. So if I put all this value, that will be 0.3775, and we are determining the output activation at H1. That is nothing but we have to consider the sigmoid function 1 divided by 1 plus e to the power minus in H1, and if I put all this value, I will be getting 0.593. And similarly, we can determine out H2 also we can determine. Corresponding to H2 also we can determine the output, that is out H2 we can determine, that is equal to 0.596. Now IN0, let us consider what is IN0. So considering the H1, H2 and the bias input, we can determine IN0, that is the input to the output layer. So we are considering now this output node, and corresponding to this output node, I am determining IN0, that is nothing but W5 into out H1 plus W6 into out H2 plus B2 into 1. So if I put this value, I will be getting this one 1.105, and we can determine the out 01 we can determine. So output we can determine corresponding to this network. Now we can determine the error. So error is nothing but the target value minus the actual output value. So that is the error, the target value minus actual output value, and if I put all this value, the error will be 0.274. So that error I have to reduce now. So I have to minimize the error. So that is corresponding to the forward pass. So now let us consider the backward pass. So corresponding to the output layer, I have to find how much change in the weight W5 affects the error E. So that is why we are considering the gradient of E with respect to W5. So we have to determine the gradient of E, that is the E is the error function, that is the cost function with respect to the weight W5, and by considering the chain rule, I can get this expression. So this delta E divided by delta out, by considering this, I can determine this differentiation. Delta out 0 divided by delta IN 0, that also I can determine, and delta IN 0 divided by delta 5, that also I can determine. So values are 0.741, 0.186 and 0.593, and finally I can determine the value, that delta E divided by delta W5, that is equal to 0.082. And similarly I can determine the weight W6 also I can determine, so that is nothing but 0.408. So like this, during the back propagation, I can determine the weights W6, W5, all the weights I can determine. And after this, let us consider the hidden layer and the input layer during the back propagation. So now we are considering the weights W1, W2, W3, W4, W3, W4. So these are the weights between the input nodes and the hidden nodes. So now we have to update the weights W1. So that is why this delta E divided by delta W1, that I am determining, and with the help of the chain rule we can obtain this. So delta E divided by delta out H1 we are determining by this expression. So we can determine, and the value is 0.55, and similarly delta out H1 divided by delta in H1, that also we can determine, that is equal to 0.241. Delta in H1 divided by delta W1, that is 0.05, and from this I can obtain delta E divided by delta W1, that is 0.006. So that is 0.006. So based on this I can determine the weights W1, W2, W3 and W4. So similarly we can find the other weights W2, W3, W4. So you can see during the back propagation I am obtaining the values of the weights, that is I am adjusting the values of the weights W1, W2, W3, W4, W5 and W6. So this is the concept of the back propagation training. So now let us discuss the concept of the vanishing gradient. So what is this problem? So the vanishing gradients in deep neural networks. So in the figure I have shown two cases, one is the training, another one is the testing, and I have shown the iterations in both the figures. So in the first case I am considering a 20 layer deep neural network, and in the second case I am considering a network having 56 layers. So corresponding to the first network, that is the 20 layered neural network, so you can see the training error. So it goes on decreasing with number of iterations. So you can see the training error corresponding to the 56 layer deep neural network, and also you can see the training error corresponding to 20 layered deep neural network. The training error is significant corresponding to 56 layered deep neural networks. Similarly, in the case of the testing also, the performance of the 56 layer neural network is not good as compared to 20 layered deep neural networks. So this is because of the problem of the vanishing gradient. So what is this problem? So for explaining this problem, let us move to the next slide. So the vanishing gradient problem. So to explain this concept, I am considering a simple network having 4 layers. So a network is considered, and this F1, F2, F3, these are the activations corresponding to these 4 layers. This is the first layer, this is the second layer, third layer, and this is the fourth layer. And input to the network is X, and I have shown the connections here, and output of the network is O. O is the output of the network, and I have to consider the weights, the connecting weights. So W1, W2, W3, W4. So these are the weights corresponding to this 4 layered network. So we are assuming that this W1, W2, W3, W4, these are scalars, and the activation functions are also scalar. So that means the corresponding output will be also scalar. So what will be the output of the network? The output of the network is O. So I can write in this form. So F4, W4, F3, W3, F2, W2, F1, W1, X, so the output of the network I can write like this. So this expression I will be getting like this. What will be the output of this node, or the output of this network corresponding to this point? So output of the network is, activation is F1 and it is W1 X. So like this I can compute the outputs of the nodes. So outputs of different layers I can compute like this, and O is the final output. So for mathematical convenience, I will be representing like this. So this W1x that I can consider as theta 1, and this W2 up to this point, this I can consider as theta 2. So this up to this point I can consider it as theta 3, and up to this point this I am considering as theta 4. This is for the mathematical convenience I am considering. So if you see this expression, what is this expression? The output of the network, that is actually F4 of W4 into F3 of W3 into F2 of W2 into F1 of W1 into X. That is the output of the network. So what is actually these outputs? the output is O. So in terms of theta, I can write like this: O is equal to F theta 4. This theta 4 is W4 F3 theta 3. This theta 3 is equal to W3 F2 theta 2. Theta 2 is equal to W2 F1 theta 1, and finally the theta 1 is equal to W1 X. So I will be getting these values, or I will be getting these outputs corresponding to the theta 1, theta 2, theta 3, theta 4. So O is equal to F4 theta 4. Theta 4 is equal to W4 into F3 of theta 3. Theta 3 is equal to W3 into F2 of theta 2, and theta 2 is equal to W2 into F1 of theta 1, and theta 1 is nothing but W1 into X. So I can get this output. So now let us move to the next slide. So again I am writing the previous equation. The previous equation I am writing again. So that is F4 W4 F3 W3 F2 W2 F1 W1 X. So the previous equation was like this, and we considered this as theta 1, this as theta 2, this as theta 3, and finally this as theta 4. So argument theta 4, argument theta 3, argument theta 2, argument theta 1 I can consider like this. This is for the mathematical convenience. So corresponding to a particular network, already I have explained during the backpropagation, I have to adjust the weights of the artificial neural network. So that is why the error is backpropagated to the input. That means the gradient is backpropagated to the input. So if I want to update a particular weight, suppose W1, then I have to determine the gradient of the output with respect to the weight W1. So the gradient I have to compute, because the gradient value is backpropagated to the input to the adjust the weights of the artificial neural network. So this is the principle of the backpropagation training. So now corresponding to this case, suppose if I want to update the weight W1, so for this I have to determine this gradient. So by using the chain rule, this del O divided by del W1, that I can write by using the chain rule, del O divided by del theta 4, del theta 4 divided by del F3 into del F3 divided by del theta 3, del theta 3 divided by del F2, del F2 divided by del theta 2, and del theta 2 divided by del F1, del F1 divided by del theta 1, and finally the del theta 1 divided by del W1. So which can be written like this: X into F1 dash into W2 into F2 dash into W3 into F3 dash into W4 into del O divided by del theta 4. So I can write like this. So this actually you can write like this. If you see this one, this is nothing but X. If you see this one, this is nothing but f1 dash. So like this I am getting these values. So all these values I am getting like this. This is for the weight W1. So I have to determine the gradient of O with respect to W1. Similarly, if I want to adjust the weight W2, I have to determine, or I have to estimate this gradient of O with respect to W2. So that is nothing but del O divided by del theta 4 into del theta 4 divided by del F3. So this is by using the chain rule, del F3 divided by del theta 3 and del theta 3 divided by del F2, del F2 divided by del theta 2 and del theta 2 divided by del W2. So corresponding to this, I can write in this form F1 into F2 dash into W3 into F3 dash into W4 into del O divided by del theta 4. So I can write in this form. So in this case, if you remember, in case of the artificial neural network, we considered the sigmoid activation function. So suppose the sigmoid activation function is fx, and if I take the differentiation of the sigmoid activation function, that is nothing but f dash x, that is equal to fx into 1 minus fx. So this is the derivative of the sigmoid activation function, and it is maximum. So it is maximum at x is equal to 0, and corresponding to this, the maximum value will be 1 by 4. So the maximum value is 1 by 4 corresponding to this sigmoid function. So it is less than 1. So if you see this expression, so we are multiplying this all the activation functions, that is the derivative of the activation function, that is the f1 dash into f2 dash. So these are mainly the derivative of the sigmoid activation function. In case of the artificial neural networks or in case of the deep networks, we randomly initialize weights during the backpropagation. During the training of the artificial neural network or the deep networks, we considered backpropagation training, and for this we randomly initialize weights of the network. So we can assume that these weights can come from a distribution function with the mean 0 and the variance 1. So I am repeating this. So weights are randomly initialized, and we can assume that these weights come from a probability distribution function with mean 0 and the variance is equal to 1. So if you see this equation, here you can see this is nothing but the product of f1 dash into f2 dash into f3 dash, and already I told you the weights are from a probability distribution function with mean 0 and the variance 1. So because of this, this product will be less than 1 and it will go on decreasing if I increase the number of layers. So as we move towards the earlier layers, for weight updation, the number of products go on increasing. So if I compare this equation number 1 and equation number 2 suppose, so number of products in equation 1 is more than the number of products in equation number 2, because we are considering the earlier layers. So I am repeating this, as we move towards the earlier layers, for weight updation, the number of products go on increasing. So because of this, since we are doing the multiplications of the sigmoid activation function, that is the derivative of the sigmoid activation function, the gradient will go on decreasing with each and every layers. So if I compare the equation number 1 and equation number 2, so the gradient value will be less in case of the equation number 1, because we are considering the earlier layer, that is W1 we are considering, that is the first layer we are considering, but in the equation number 2 we are considering the second layer. So as we move towards earlier layers, the number of products go on increasing. So that is the concept of the vanishing gradient. So the gradient value will go on decreasing. So what is the weight updation rule? So what is the weight updation rule? If you remember that weight updation rule, So we have considered this weight updation rule. So Wt plus 1, that is the weight at the t plus 1 iteration, and this is the weight in the tth iteration minus the learning rate eta, and we are computing the gradient. So we are computing the gradient. So since this gradient value will go on decreasing, so this value will go on decreasing, then what will happen? The weight at t plus 1 iteration will be same as that of the weight at the tth iteration. So I am repeating this. Since the gradient of W, it will go on decreasing with increasing number of layers, so that is why the weight at t plus 1 iteration will be not updated, because it will be same as that of the weight at the tth iteration. So this will be negligible, this term will be negligible, because the gradient of the W, that will be very small. So that is why the weight will not be updated. The weight at the t plus 1 iteration will be same as that of the weight at tth iteration. So weight at t plus 1 iteration will be same as that of the weight at tth iteration. That means the weights will not be updated, because the gradient value will go on decreasing with increased number of layers. So if I increase the number of layers, the gradient value will go on decreasing because of this problem. And the opposite is the exploding gradient. So if the gradient value is very high, so what will happen? It will go on increasing, and because of this, it is very difficult to get the convergence condition, and the oscillations will take place. So that is the concept of the exploding gradient. That is the opposite of the vanishing gradient. In the vanishing gradient, because of the number of layers, if I increase the number of layers, the gradient value will go on decreasing, and because of this, the weight will not be updated, the weights will not be updated. But in case of the exploding gradient, the gradient value is greater than 1, and because of this, the gradient value will go on increasing, and because of this, it is difficult to get the convergence condition, and the oscillation will take place. So how to consider this issue and this vanishing gradient problem? So how to consider this issue? So let us move to the next slide. So to consider this issue, how to consider? So first point is the choice of activation function ReLU instead of sigmoid function. Instead of the sigmoidal function. So in case of the deep networks, we are considering more number of layers as compared to artificial neural networks, because we are considering the deep architecture. So to consider this problem, the problem of the vanishing gradient, we may consider ReLU activation function instead of the sigmoidal activation function. So that is one option. The second also, what we can consider, appropriate initialization of weights. So suppose I have a network, so n number of terminals are there. So now how to consider the appropriate weights? So in this case, we can consider the distribution, zero mean distribution we can consider, but variance we can consider as 1 by n we can consider. So in the earlier case, we considered the variance is 1 corresponding to this distribution, because the randomly we are initializing the weights, and corresponding to this, we can assume that these weights are coming from a probability distribution function with mean 0 and variance 1. But in this case, what we are considering, the distribution having the mean 0 and the variance is equal to 1 by n, and sometimes also 2 by n is also considered. So either 1 by n or 2 by n we can consider for this initialization of the weights. So variance will be 1 by n or the 2 by n, and the mean will be 0. And finally, another technique is that I am not going to discuss, that is the intelligent the back propagation learning algorithm. So we may employ this technique, that is the intelligent backpropagation learning algorithm we can also consider. So with the help of these techniques, that is the one important technique is the ReLU function, ReLU activation function we can consider instead of the sigmoidal activation function. That is why the ReLU function is popular in case of the deep neural networks instead of the sigmoidal activation function. In this class, I explained the concept of the backpropagation training, and also I explain the problem of the vanishing gradient and the exploding gradient. So if I increase the number of layers of a particular network, the performance of the network may not improve because of the problem of the vanishing gradient and the exploding gradient. To consider this issue, we may consider the ReLU activation function instead of the sigmoidal activation function. Also, we can appropriately select the weights of the network that already I have explained, and also we can consider the intelligent backpropagation algorithm. So these are the techniques to consider the vanishing gradient problem or the exploding gradient problem. So let me stop here today. Thank you.